Hi there everybody, this is Mr. Neil here to go over the last couple of things on speed and velocity before I cover accelerated motion. And in this last couple of things, let me switch to our little canvas here. We've been looking at constant speed. So on position time graphs we had fairly straight lines. We had positive, we had negative, we had not moving at all, so constant and flat. Those are all very simple cases. But when we're talking about a real life situation, speed does not actually remain constant all the time. If you're looking at your speedometer in the car at one moment in time and then look at it a few moments later, unless you have very good control over your foot, your speed is probably fluctuating from moment to moment. Not by a lot, but by a little bit. And ignoring even those little tiny changes, you have traffic lights that you have to slow down for, stop for, or traffic jams. You've got all sorts of things that necessitate changing your speed continuously throughout your trip. So what does this mean for calculating speed? Well, there's two different types of speed that we care about. The first kind, the kind that we've really been dealing with other than constant, is what we call instantaneous speed. And instantaneous speed is speed at that moment. So if you look at your speedometer readings, let's say this one is 55 miles per hour and this one is 45 miles per hour. Those are examples of instantaneous speeds at that instant in time. If you look over your entire trip, however, and you want to know how fast you would have to go if you could travel in a straight line just between the 2 points, that's what we call our average speed. Or I shouldn't say a straight line between the 2 points, but without stopping at all. Our average speed is total distance divided by total time of travel. So you could have points in time where you're traveling really slowly, say maybe you're slowing down for traffic, and points in time where maybe the highway is free and clear and you accelerate so that you're traveling at higher speed. Your average speed is the speed that you would have to travel at one value to go the entire journey of the trip at that rate. So the total distance over the total time. And the average speed will always be somewhere in between your low speed and your high speed. This is because it's an average. It has to be somewhere in between them. So if you calculate average speed, it can never be higher than your highest and never lower than your lowest. Pretty straightforward. Okay? Well, let's continue this. Our velocity is slightly different from speed. And the only thing that is different from speed is the fact that we have a directional component, which is why we are drawing this thing as a vector instead of just a number. So 55 miles per hour to the west would be an example of a velocity, because not only do you have this 55 miles per hour, you can add in this westerly vector, although if I'm to be doing this precisely because you're looking at this on the projector screen, I should probably change this to point in the opposite direction. And this would be 55 miles per hour. And velocity is simply our displacement over our time. And if you like our triangle that we've been using, here it is. V equals d over t. But this means there's actually two ways of changing our velocity. We talked about them, I believe, a little bit last week, but we didn't go into any detail. But let's take an example here. Let's draw a circular track, or a roughly circular track here, and consider 4 different positions on this track. So this will be position 1, this will be position 2, this will be position 3, and this will be position 4. Now let's say this vehicle, or this object, is traveling at a constant speed of 10 meters per second. Well, what that means is if I draw in the velocity vectors at each of these 4 points, and let's say we're going counterclockwise here. On this point in the track, I'm driving in this direction, and so my velocity points in this direction, 10 meters per second. At point 2, I'm driving towards the bottom of the screen, so my velocity vector is the same size, but now it's pointed in a different direction. Again, point 3, 10 meters per second, vector is the same size as before, but now it's pointed towards the right of the screen. And finally, point 4, 10 meters per second, it's the same size as the other 3 vectors, but now it's pointed towards the top of the screen. These arrows, these vectors, are changing direction. They're never pointed in the same direction. And if velocity incorporates direction, then any one of these is a different velocity. Even though they're at a constant speed, the velocity is changing, or what we would represent as a delta V. So, although you can travel at a constant speed in a circle, you can't travel at a constant velocity, because just changing the direction of your travel changes the velocity that you're traveling at. And this is going to be really important when we're talking about acceleration, because, let's make a new screen here. Acceleration is any change in velocity, which I'll just represent with a delta V, change in velocity. Which means there are 3 different ways that you can accelerate. Number 1, the familiar way. You can go faster. Number 2, the other familiar way, but you would call it decelerating. You can go slower. These 2 represent changes in speed. But there is a third way. Because velocity is a vector, all you have to do to accelerate is change your direction. This could be as simple as turning. A simple change in direction changes the velocity. These also change the velocity, but they change it by changing the speed component. The third one changes the velocity by changing the vector component, the direction component, which means you can go faster, go slower, or change your direction in order to change your velocity and therefore accelerate. Now there is an equation that you'll need to know for acceleration. It is in the reference tables, and that equation is acceleration is equal to the change in velocity over the change in time. Now again, I'm going to draw them with little vectors over the top so you can actually see that they're vectors. It's just a little reminder to you that they're vectors. Alright, and remember delta is change in, or final, minus initial. I'm not going to do the same thing for time, even though it is technically there, because in 90% of acceleration problems, this time is given to you as a period of time, aka they give you delta t in the problem. So there's no need to calculate the change in time 90% of the time. Okay, so let's actually look at what units we would need for acceleration before I go and do a couple of examples here. Now, because acceleration is a change in velocity over a period of time, I need units of velocity on top and units of time on the bottom. Now, most commonly in metric, our velocity is given in meters per second, and our time would be given in seconds. So we could leave it like this, meters per second, or it would be equally valid, because these are both the same unit, to say meters per second squared. That's a perfectly valid unit, and indeed this is the most common way that you will see it. However, there are accelerations that don't have the same unit of time. For example, cars. When you're looking at a car, your speed is given in units of miles per hour. But your acceleration takes place over a period of seconds, not hours. And so our unit of time would be seconds. And we wind up with the odd-looking unit, miles per hour per second. Or I could rewrite it like this, so it would look like the metric version, miles per hour per second. That's a perfectly valid unit for acceleration as well, because we have a velocity component and we have a time component that are being divided together, and velocity over time gives us the acceleration. So if we were looking back at the graphs that we created at the beginning, and we had a position time graph that looked like this, recall that this would give us a velocity time graph which looks like this. These represent a constant positive acceleration. So, for example, let's say I start at 0 meters per second, and I'm going to accelerate at a rate of 1 meter per second squared. So in the first time period, let's make a little table here. We'll call this time 0. And we'll have a table of velocities over here. After 1 second, I'm moving at 1 meter per second. I've added 1. After 2 seconds, I'm moving at 2 meters per second. Again, I've added 1. After 3 seconds, I'm moving at 3 meters per second. Again, I'm adding 1. What am I adding 1 of? I'm adding 1 meter per second to my speed for every second of travel. So that's what this means. I add 1 meter per second to speed for every 1 second of travel, because it's a rate of change of my velocity, not my position. So it's actually the rate of change of a rate of change, which is kind of confusing, I know. That's why we have these weird looking units, and why we wind up with a curved graph on our position time. Alright, you could actually, and you don't have to do it for this class, but I just want to show you, if you graphed the slope of velocity time, just like we graphed the slope of position time, you would wind up graphing acceleration. And the graph over here of acceleration over time would be a flat line. There's a pattern there. Okay. Second kind of curve that we looked at that could be acceleration was negative acceleration, where you're actually slowing down over time. So the graph looks like this for velocity time. And if we did the acceleration graph, just like the velocity graph was a flat horizontal line, for this slope, it becomes a flat horizontal line for that acceleration. Just wanted to show you that it is a constant uniform acceleration. Either one of these graphs, or any one of these graphs, represents a graph of accelerated motion, which you will need to be able to identify. Okay, so let's look at some example problems for calculating acceleration.